Alrighty folks, we're going to do a quick video here on understanding how to locate holes in the graphs of rational functions. Now, you've already seen a video on how to identify where the x-coordinate is for a hole. But what we want to do now is, if we want to graph a rational function on a coordinate plane, we don't just want to know the x-coordinate of the hole, we want to know exactly where on the coordinate plane, where is the hole. And so, really it's just a matter of taking the x value and plugging it back into the function, but you have to plug it in after you have crossed out the factor. So let's say we have this rational function and we want to identify where all of the holes are in this function. Okay, so the first thing we want to do is we want to factor the rational function. Okay, so this is going to become, looks like I can factor a 4 out here, a greatest common factor. So I'm going to take out a 4, and that's going to leave me with x squared minus 2x minus 3. Okay, and then down here I can factor this. Two numbers that multiply to positive 3 but add up to negative 4 are negative 1 and negative 3. So this is going to become x minus 1 and x times x minus 3, right? And let's go back up to the numerator. We're going to factor this quadratic here. We want two numbers that multiply to negative 3, but they add up to negative 2. So those two numbers would be negative 3 and positive 1. Okay, so let me kind of cross this out, and I'm going to put x minus 3 times x plus 1. So now, and don't forget that 4 is there, so it's 4 times x minus 3 times x plus 1. Now that we have factored the numerator and the denominator, now we can cross out any matching binomials. And you'll see here, we've got an x minus 3 here and an x minus 3 here. So we're going to cross those out. Now what does that mean? What does that tell us about the hole? That tells us that there is a hole at x equals 3. Because if we take the factor that was crossed out, x minus 3, set it equal to 0, and then solve, we would get x equals 3. And that tells us that if we were to plug a 3 in, what would that do to the denominator? It would give us 0. What would that do to the numerator? It would also give us 0, and we would have 0 over 0. And 0 over 0 is the indicator that you have found a hole. Okay? So we know that because we crossed out x minus 3, that gives us a hole at x equals positive 3. Now what we're going to do is this. We're going to take the 4 times x plus 1 over x minus 1. And the reason we only have this left is because we crossed out the x minus 3. Once you have crossed out all of the holes, now you can identify where the y-coordinate for the hole. Because now when we plug the 3 in, we won't get 0 over 0. We'll get a real number. Okay? So if we put a 3 in here, we get x plus 1. So you have 4 times 3 is x. So 4 times 3 plus 1 over, put the 3 in down here, 3 minus 1. All right, equals 3 plus 1, that's 4. 4 times 4 is 16. 3 minus 1 is 2, and 16 over 2 is 8. And so the y-coordinate for the hole is 8. And therefore, this hole, the hole that's in this rational function, is at the coordinates 3 and 8. So I can go over to a coordinate plane now, and I can go 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, and I can put a big open circle there indicating that there is a hole in the function at that point. Okay? Let's try another one. All right, here's another one for you. Why don't you pause the video and see if you can find out the coordinates of this hole in this rational function. All right, so the first thing we're going to want to do is we're going to want to factor the numerator and the denominator, right? Well, it looks like I have a 3 in here that I can factor out. So if I factor out a 3, actually let me do it up here. That would be 3 times x squared. 27 divided by 3 is 9, so plus 9x. 42 divided by 3, that's what, 14? So plus 14. There we go. All right, now I got to think of what are two numbers that multiply to 14 but add up to positive 9. 7 and 2. All right, positive 7, positive 2. So this is going to be 3 times x plus 7 times x plus 2 over two numbers that multiply to negative 16, but they add up to negative 6. So what multiplies to negative 16? How about negative 8 and positive 2? Because negative 8 plus 2 is negative 6, and negative 8 times 2 is negative 16. So it's going to be x minus 8 times x plus 2. And sure enough, we've got a hole here. Remember, the way we know we have a hole is if we have a matching factor in the numerator and the denominator. So we've got an x plus 2 in the numerator and an x plus 2 in the denominator. So we're going to cancel that out. Meaning we have a hole at x equals negative 2. Now we're just simply going to plug the negative 2 into what's left over. So we're going to put a negative 2 here. We've got negative 2 plus 7. So we'd have 3 times negative 2 plus 7 over, now we're going to put the negative 2 down here, negative 2 minus 8, negative 2 minus 8. Negative 2 plus 7, that's 5. 5 times 3 is 15. Over negative 2 minus 8 is negative 10. All right, so this is going to be y equals 15 over negative 10, and a positive divided by a negative is a negative, and 15 over 10, that can be reduced to 3 over 2. So negative 3 over 2. And so the coordinates of the hole in this function are at negative 2 and negative 3 over 2. Okay? And so now I can go to a coordinate plane, and I can go to negative 2, and then to negative 3 over 2. Negative 3 over 2 is negative 1 1/2. Negative 1 1/2, and right here, put an open circle. I probably made that open circle too big, but I wanted you to be able to see it on the video. But there we go. There's a hole in the function. And that's it. All right? That's how you identify the coordinates of a hole in a rational function. In the next video, we're going to pull all this stuff that we've learned about graphs of rational functions. We're going to put it together, and we are actually going to draw a picture of rational functions.